Welcome students. Today in this video, I'm going to discuss about electrostatic, which is one of the topic of CPH 302. Let us start with the concepts of field, the scalar field, vector field, and differential calculus. Okay. First and the foremost things which comes to our mind is that what is field? If you talk about field, the field of a physical quantity is a region in space which has been modified by the presence of a physical quantity. Now the question arises is, what is a physical quantity? So if you talk about physical quantity are the terms through which the law of physics can be explained. Or in other words, we can say that these are the quantities which can be measured directly or indirectly. Okay, so the field, the region which it modifies. If you talk about any physical quantity, as for example, suppose I talk about charge, I talk about charge, I talk about charge. Okay, so charge is what? Charge is a physical quantity, right? So what happens if you talk about charge? This charge, what is going to do? It is going to modify its space around itself. Okay, so this is what is a field is. Okay, or I can say that field of a physical quantity. Okay, so field is what? So it is a region which is a region in space which has been modified by the presence of a physical quantity. Okay, now the most important thing is this: all physical quantity, they depends on the particle position. Okay, all the physical quantities, they depend on the particle position. Now this I'm going to explain you in my further slides, that what do I mean by saying that. Okay, so when we talk about physical quantity, we are aware of it. I think in 9th standard you might have studied that physical quantities, these are classified into two different quantities. One is called scalar, another one is called vector quantities. Now, when you talk about scalar quantities are those quantities which has only magnitude associated with them. What do I mean by saying that? They don't have direction associated with them. Now, suppose if you say I'm talking about time. So, if someone is asking you, time is a physical quantity. Now, if I ask you, time, what is the time? I will say it is 10:30 a.m. or 10:30 p.m. But I will not say that 10:30 a.m. it is in the east direction. No such things. So what happened? It is specific. So it is associated only with its magnitude, not with the direction. So those physical quantities which has only magnitude associated with it, these are called as the scalar quantities. Whereas if you talk about the vector quantities, then what do we find? That in vector quantity depends both on magnitude as well as direction. Okay, so it will have magnitude as well as direction. For example, suppose if you talk about the electric field. Okay, now which I am going to talk about it, electric field. Now electric field is what? It has magnitude as well as direction associated with it. One more thing about, so based on that, now as the name suggests, we are going to talk about scalar field and vector field. So definite thing which comes into our mind is this: when we talk about scalar field, we are going to talk about what? We are going to talk about the scalar quantity here. Okay, whenever the scalar quantities are involved, we will talk about scalar field. Whenever the vector quantities are involved, we are going to talk about the vector field. Okay, so that is what. Now, one thing which I have mentioned you, I said that if you talk about the field, then all the physical quantity, they depend on the particle position. Okay, what do I mean by saying that? Now, suppose you say that you are having a charge. Okay, a charge Q, say. Now, what does it do? That Q, what will it do? It will modify the space around itself, right? The charge is going to do what? That charge is going to modify the space around itself. Okay, now and in that space what happens? Suppose you say within that space we are taking any other point and I want to find out the electric potential. Okay, so what will happen? We know if you talk about electric potential, the formula to calculate the electric potential V is equal to 1 by 4 pi epsilon naught 1 divided by R. Where what does R stands for? R stands for the distance, right? Distance from the charge. Okay, so what happened? The moment we find that it is associated with distance, the electric potential, it is dependent upon the distance. What does it imply? That at different distances, the value of the electric potential will be different. Means I'm having a charge. it has modifies the space around itself, and within that space we are having so many different points, and in each point what is happening, the value of the potential is different. Why it will be different? Because the value of potential is dependent upon the distance. So that is the reason what we say that in the region of space, that is the field which I am talking about, the physical quantity which we are taking, that is continuous and single valued at every point. Okay, so this is the meaning of saying this statement, that if you talk about the region of the space, that means if you talk about the field, okay, so if you talk about the field, the physical quantity within that field is continuous and single valued at every point. Okay, so based on that, we are going to talk about now what is a scalar field. Okay, now see, I'm having a charge. The charge has modified the space around itself. Clear? I'm taking a scalar function, a scalar quantity, say electric potential. But electric potential is a scalar quantity. So what happened is that now the charge modifies the space around itself. Clear? Now after that, what has happened, if you consider any point within that field, the value of potential is going to be different. Correct with it? So what can I say that, you know, if you talk about, so how will I define the scalar field? So I will say the field is said to be scalar field if the quantity involved is a scalar one. Okay, so if the quantity involved is a scalar one. Correct with it? So what happened is this, like electric potential is a scalar quantity. So what will happen, the field that is associated with that electric potential, we will call it as a scalar field. Okay, and as I said, each point of a scalar field will represent what? A scalar. That is the value of the quantity. If you talk about the value of the quantity at a particular point, okay, is same regardless of the direction. Okay, regardless of the direction, it will not depend on the direction. Okay, you are talking about the field. Within that field, we are taking different points. In the different points, what is happening? The value of the electric potential is different. Okay, so this is what you will have to take care of. Clear to all the student? Okay, so as a result of which, what will happen is this. So I am, so we can say, if you talk about the temperature of a place, electric potential, gravitational potential, all these are examples of what we call as the scalar field. Okay, I hope the scalar field, it is clear to you. Or in other words, I can say that a region where the scalar physical quantity has a unique value at each point. Okay, so that is what is a scalar. That is what is a scalar field. Okay, or you can say that this is what do we mean by saying a scalar field. Clear to all the student? Okay. So always keep it in mind that whenever we talk about the scalar field, there at every point within that field, the value will be unique. Unique means it will be different. Okay, clear to you? Okay, so next we are going to talk about what is called as your vector field. Okay, now vector field, as the name suggests, when we talk about vector field, okay, vector field means what? If the quantity which we are talking about, okay, the quantity which we are talking about, it is a vector quantity, okay, then the field that we are going to get, that is what is called as a, that we will call as a vector field. Okay, that field is called as a vector field. Okay, now let us talk about it in a little details. Okay, now say I talk about the electric field. So same way, when I talk about, I'm considering a charge. Charge is modifying the space around itself. I want to find the value of the electric field at different position. Now what do I know? Okay, I know that what is electric field. What is the formula to calculate the electric field? The formula to calculate the electric field is equal to force by charge. Okay, force by charge. Now it can also be written as E is equal to 1 by 4 pi epsilon naught Q by R multiplied by a unit vector. Correct with it? Now I'm having a charge and I'm considering a point A within the field produced by that charge. I'm considering the electric field. Now, if the charge is positive, now electric field is always directed outward. That we are knowing. If it is negative, it will be inward. But if it is positive, it is outward. Correct with it? So that means it is depending upon the direction. Clear to all the students? Okay, so it is going to depend upon direction. I'm considering two different points within the field. Okay, a point A and another one is a point B. Okay, now point A is nearer to the charge, point B it is a little farther to the charge. Then what will happen? It is so obvious that what we are knowing, that electric field is inversely proportional to the distance, square of the distance. So what can I say about it? I can say that the field at A will definitely be greater than the field at B. Clear to you? So what can I say, that in this case the quantity which I have considered, that is a vector. Okay, so what will happen? The field that we are going to get, that is considered as a vector field. Okay, so a vector field is a construction which associate each point, okay, x, y, z in space to a vector. Now this is very important, you'll have to keep it in mind. The moment I talk about vector field, I'll have to consider direction. Okay, now if you talk about vector, a vector does not have any position. A vector has no position. So what will happen? We always indicate a vector field in the graphical form by placing a vector v bar with its tail at x, y, z. Okay, this you will have to keep it in mind, and this will become more clear as I move on for my next slide, where I'm going to talk about the derivative of a function, where I'm going to talk about the gradient of a function. We are going to talk about the divergence. Okay, at that time it will become more and more clear what I mean by saying that, because we don't have a single no position associated with it, so we always indicate it by the position vector, where we are having a tail and a head. Okay, we represent the quantity by its position vector. Okay, so the gravitational field, if you talk about the electric field, if you talk about the magnetic field, if you talk about, all these are the examples of the vector field. Okay, so this is what is about a vector field. So we are having field, two type of field I have discussed, scalar field and vector field. Now the next part which I am going to talk about is your ordinary derivative. Okay, what is ordinary derivative? Okay, I can also call it by the name. What do I mean by saying derivative of a vector? Okay, that also I'm going to talk about. Okay, now if you talk about the ordinary derivative of a function of single variable, now what do I mean by saying that? Okay, single variable means what? Suppose you say that f of x I have written. F of x means what? F is a function of x. Means f is dependent upon the value of x. Okay. So ordinary derivative of a function of a single variable. Okay. F of x is represented as what? Df by dx. Now what does it give? What is the meaning of saying df by dx? Now what does it give? It gives us df. What is df? D stands for the variation. So it gives us what? It gives us the variation in fx as we change the argument x by a tiny amount dx. Clear to all of you? Okay. So what we are going to talk about, if I say f of x, so f of x is represented as what? Df by dx. And what does it give? It gives us df, that is the variation of f as we change the argument of x by a tiny amount dx. Clear to all of you? Means as I am changing dx, okay, how my function is varying, that is what is called as an ordinary derivative. Okay, if the function varies slowly with x, okay, then the derivative which I am talking about, that will be correspondingly small. Okay, but if it changes rapidly with the change in x, the derivative is said to be large derivative. Okay, now I'll just talk more about it. Suppose you say that I'm having a vector e, okay, and say the vector e is a function of a scalar quantity. Okay, say t. Okay, like here the way I mentioned, I'm saying that f of x. So instead of f, I'm talking about a vector, say e. Okay, and instead of x, I'm saying that function is a vector of a scalar quantity, say t. Okay, that means the value of e depends upon what? The value of t. That means I can say that e is equal to e of t. Clear to you? Okay, now initial value of initial value will be what? Et. Okay, now if I increase the time, not time, increase the scalar quantity t, say, okay, increase in the value of t by a small amount delta t. Okay, so I will say what is the increase? T plus delta t. So accordingly, what will happen? Your vector, the value of the vector is also going to change. It will be E of t plus delta t. Okay, E of t plus delta t. Then what is the change in E? The change in E will be equal to E of t plus delta t minus Et. Okay, now if you divide this delta E by delta t, that is going to give you what? That is going to give you the derivative of the function. Okay, clear to you? Okay, now what will happen if you say that the value of delta E upon delta t, okay, if you consider the value of delta E upon delta t in a limiting case. What do I mean by saying limiting case? Limiting case means that if I say that when delta t is tending to 0 but it is not equal to 0, means that the value of the delta t is very small. Now as I said, if the function varies just slowly, okay, so same way it means the same. If I say that the value of if delta t tends to 0, okay, then what will I say? Delta E upon delta t is called as the derivative of E with respect to t. I will consider it to be derivative of E with respect to t. So as I have already mentioned you, so if you talk about the ordinary derivative will be represented by df by dx. Now x may change. Suppose you say my function is varying with y-axis. Okay, my function is whatever it will totally depends upon the variable is what. Okay, so you will have to consider, suppose as I mentioned you that E is a function of scalar quantity. Okay, so same way I'm talking about f and I'm talking about f is a function of t. Suppose you say f is a function of a scalar quantity t, then I will represent the derivative as df by dt instead of x. Okay, like here in this particular here what I have mentioned is this. I have said I have said that f of x is represented as df by dx, means f is a function of x. If I say f is a function of t, what will I write? I will write df upon dt. Okay, so this is what is about your ordinary derivative. Okay, now the question arises, if you talk about ordinary derivative, what is the geometrical interpretation? If I talk about what is the geometrical interpretation of this df by dt, now if you talk about the derivative df by dx, okay, it gives you what? It is the slope of graph of f versus x. Okay, if I say df by dt, then I will say it will be the slope of graph of f versus t. Means how my function is varying with x, the slope of the graph, okay, gives you the value of the derivative. So if you want to, that is the reason I said geometrical interpretation. If you talk about geometrical interpretation, when I talk about geometrical interpretation, what is the meaning of geometrical interpretation? The meaning of geometrical interpretation is that I'm having a derivative, okay, I'm having the derivative. I have already found out the derivative df upon dx. Okay, now if I talk about geometrical interpretation, what we will do, we will plot the variation of f with respect to x, and the slope of the graph, whatever we are going to get, that is going to give you the value of the derivative. Okay, so this is the geometrical interpretation. Okay, now if I say what about the three-dimensional derivative, what do I mean by saying three-dimensional derivative? Now if you have three dimension, if you are considering three dimension x, y and z, same. Okay, so in case of three dimension, we have infinite number of direction. Okay, infinite number of direction. So in three dimension, okay, we have to take care of direction also, which can be represented by just three variables. Okay, so what will happen in 3D, we have to care of what? Direction also. So which can be represented by three variables. What are those three variables? X, Y, Z in Cartesian system, R, theta, phi in spherical system, and R, theta, Z in cylindrical system. Okay, here we are going to talk only about the Cartesian system. Okay, like because as I said in my upcoming slides, also in my upcoming videos, I'm going to discuss more about we are going to talk about the gradient of a vector. We are going to talk about the divergence of a vector. Okay, in my upcoming videos, I'm going to share all those things with it. I'm going to talk about the divergence of a vector. I'm going to talk about the curl of a vector, right? So in all these things, what happen if you talk about, in all those things, we are going to take about the Cartesian coordinate. Okay, now if you talk about in 3D, okay, in 3D, the derivative of a function means the function, it is depending upon x also, y also, z also. In that case, I will represent it as delta f. Okay, this triangle which you get, this inverted triangle which we say. So this inverted triangle is represent what? We will call it as delta f. So delta f. So but this is pronounced as what? Nabla. We can also call it as nabla, and it is given by what? This nabla is equal to I car del by del x plus j car del by del y plus k car del by del z. Okay, so this is the meaning of this term. Now this can be operated in three different ways. Operation with delta. Okay, what are the operations? Simply you say delta into t. Okay, I'm not writing any dot, cross, nothing. This has a different meaning in physics. Now if I say delta t is a scalar function. Now this delta t, it will be called as gradient of a scalar. Okay, now here is a delta v, delta dot v. Here v should be a scalar quantity. When I'm writing this dot with this delta, in that case this v will have to be a vector quantity. I cannot write this delta dot t. I cannot write a scalar quantity. Okay, so delta dot v, v is what? V is a vector quantity, and delta dot delta cross v, that is v is a vector quantity. So these are the different operations which I'm going to talk about in my upcoming videos. Okay, thank you for watching.